Welcome back, everybody. Today, we're going deep, really deep into operating
Oh,
systems,
yeah.
and specifically how they manage the programs we use every single day.
Right.
Have you ever thought about, like, when you click an icon,
Oh, yeah.
what happens?
Absolutely.
Your computer starts doing this elaborate dance of resources and instructions.
That's a great way to put it, yeah.
So we're gonna decode that dance using our guide here, OS Part 3, processes and threads.pdf.
Perfect.
So to kick things off, what is a process?
Ah, good question.
I mean, we throw that word around
Yeah, yeah.
in tech a lot,
All the time, yeah.
but what does it actually mean in the context of an operating system?
Well, I think one of the best ways to think about this is by using an analogy.
Okay.
So think of a process like a dedicated chef working on a specific dish.
Okay.
They have their own set of ingredients representing memory,
Yeah.
the tools symbolizing the CPU,
Mhm.
and of course, they have the recipe, which are the instructions the process needs to execute.
So every time I open a program, it's like a new chef coming into the kitchen.
Precisely. Every single program that you run becomes a process, and that process is managed by the operating system.
Wow. So my computer is like a really busy kitchen
Yeah, that's a great way to think
with
about it.
all these chefs running around.
Yeah, absolutely.
So if we look at this diagram here, processes, state machine view,
Yeah,
our chef can be running, ready, blocked,
right.
or even terminating.
Exactly.
It's like they're taking a break, or they're waiting for something,
Yeah.
or they're actively cooking.
Yeah, and it's really fascinating because tools like Top actually give us a little glimpse into this hidden world, so
Uh-huh.
we can actually observe the state of each process, how much CPU they're using, what resources it's holding on to.
Oh, that's cool.
It's really neat.
So it's like I can see what each chef is doing at
Absolutely.
any given time.
At any given time. Yeah.
Now, what happens when you've got all these chefs
Yeah.
and they all want to use the same stove at the same time?
Right.
Like, things could get pretty chaotic.
Absolutely. That's where the operating system steps in
Okay.
and plays the role of master coordinator.
Okay.
So if we take a look at this diagram here, processes, queuing model view.
Okay.
This illustrates how processes waiting for resources form these queues.
Okay.
Right. And the operating system uses different queuing strategies to kind of manage these lines and make sure everything runs smoothly.
So it's like there's a system in place
Exactly.
so that chefs aren't just, running into each other and
Exactly.
grabbing stuff.
Yeah. And have you ever noticed, like, if you have a ton of programs open,
Uh-huh.
that your computer starts to slow down?
Yeah, yeah.
That's basically this queuing model getting a bit backed up.
Oh, okay.
Too many chefs, not enough stoves.
So the operating system is like the head chef making sure everything is
Absolutely.
organized and running smoothly.
That's a great way to think about it.
But how does it keep track of all these processes and their individual needs?
Right.
Like, it's like having a mental checklist for every chef in the kitchen.
Exactly. So this is where the process control block comes into play, or as it's more commonly called, the PCB.
Okay.
So think of it like a detailed dossier
Okay.
for each process.
Okay.
So if we pull up the diagram here, process control block,
Okay.
we can see it contains essential information such as the process ID,
Okay.
its current state,
Mm-hmm.
saved registers, memory details, and even pointers to other PCBs.
So this PCB, it's like the head chef
Uh.
has a file folder for each chef
Yes,
in the kitchen
exactly.
containing, their name, their experience level,
Yeah,
what they're currently working on,
absolutely.
and even, notes about how they interact with other chefs.
That's a great way to think about it.
Okay.
And to make things even more organized, these PCBs are often grouped together into process lists.
Okay.
And this allows the operating system to really efficiently manage and track all the active processes running on the system.
So it's like all these chef files are neatly arranged in a filing cabinet,
Yes, yes.
categorized by maybe, their specialty or what they're currently working on.
That's a great analogy.
Okay, now what happens if two chefs need to access the same, like, ingredient list
Right.
at the same time?
Yeah,
Could that cause problems?
absolutely. So this is where the concept of locks comes in.
Okay.
So imagine there's like a lock on the refrigerator door.
Okay.
That ensures only one chef can access the ingredients at any given time.
Okay.
In operating systems, this concept of locks, it's implemented to prevent conflicts and ensure that shared resources are being accessed, in an orderly fashion.
So locks are kind of like traffic signals
Yes,
in a computer city. They make sure that everything flows smoothly.
prevents collision.
Yeah, prevents collisions.
Yeah.
Okay, now that we kind of have a handle on how the operating system keeps track of all these processes,
Yeah,
let's talk about how these processes come into existence.
right.
I see a diagram here labeled process creation fork.
Yes,
Does that have something to do with it?
absolutely. So, fork is the way that a new process is created from an existing one.
Okay.
So, picture it like a cell dividing.
Uh-huh.
So, one process splits into two. The original process becomes the parent, and the new process becomes the child.
Okay.
Now, what's really interesting is both the parent and child processes, they can continue to do their work, they
Yeah.
can share some resources, but ultimately they have their own distinct paths.
So it's like a culinary dynasty.
Yes.
You've got the master chef,
Yep.
and then they train an apprentice.
Exactly.
And they both kind of go their own way.
Yeah. And they both contribute to the overall culinary experience.
Okay, what if a chef wants to try a totally different dish?
Right.
But they want to use the same kitchen and tools.
Yeah.
Is that possible?
Absolutely. And that's where exec comes into play.
Okay.
So think of exec as like a chef swapping out their recipe, but keeping the same kitchen and tools.
Okay.
So essentially what exec does is it allows a process to load a new program into its memory space. It's basically replacing the old instructions with a new set.
Okay.
So no need to build a new kitchen.
Gotcha. So no new kitchen, just a new recipe.
Exactly.
Okay. Now, all good things must come to an end, right?
They do.
What happens when a process, it's finished its work?
Right. So eventually every process needs to say goodbye.
Okay.
And if we take a look at the process termination diagram,
Okay.
this kind of illustrates the idea of a process exiting gracefully. And we do this using the exit system call.
So exit is like the chef's sign-off sheet.
Exactly.
They're like, okay, I'm done with my work.
Yeah.
Clocking out.
Absolutely.
See ya. Now, what about the parent process?
Right.
Does the parent process know when its child process is finished working?
Absolutely. So a parent process can actually use what's called the wait system call.
Okay.
And this allows the parent process to patiently wait for its child process to finish
Okay.
before it continues its own execution.
So it's kind of like the head chef is checking in
Yes.
with the apprentice. They're like,
Absolutely.
all right, is your dish ready?
Exactly.
Before we serve everything.
Before we open the restaurant.
Yeah, before we open the restaurant. Okay, so this wait system call, it keeps things synchronized.
Yeah.
And it makes sure that everything's running smoothly.
Absolutely. Yeah.
But with all this creating and terminating, how does the operating system keep track of all these relationships between these processes?
So that's where the concept of process trees come into play.
Okay.
So imagine a family tree, but instead of, family members, it's all the processes.
Okay.
So as new processes are created via this fork that we were talking about before,
Right.
they branch out from their parent process, forming this really neat hierarchical tree structure.
So it's like a culinary lineage.
Yes.
We can trace, who trained who
Exactly.
and how these different chefs are related to each other.
Absolutely.
Okay, so we've got this process tree diagram here.
Right.
It really illustrates that nicely.
It does. It does.
Now, what happens if a parent process terminates,
Right.
but its child processes are still running?
Right.
Do they become orphans?
Yeah, so that's a great question. And operating systems, they have different ways of handling this. Some operating systems, what they'll do is they'll reassign those child processes to a new parent. So it's kind of like they're adopted into a new culinary family.
Right.
But some operating systems, they might terminate them along with the parent. So it's kind of like closing down the entire restaurant.
Oh, wow.
So it all depends on the operating system itself and its policies.
Okay, so it's kind of like there's a backup plan in place.
Yeah, exactly.
Just in case the head chef suddenly, disappears.
Right.
Okay, so we've been talking a lot about these system calls.
We have.
Like fork and exec and exit and wait.
Right.
But I bet our listeners are wondering, like, how do programmers actually use these
Right.
in their code
Yeah, great question.
to manage these processes?
Yeah, so let's actually take a peek under the hood and look at some code.
Okay.
And we'll start with something called the POSS API. And this provides a standardized set of system calls that programmers can use to manage processes. And it works across different Unix-like operating systems.
So the PO6 API is kind of like a universal language
It is.
that the programmers use to talk to the operating system.
Exactly.
Wait, I see here we've got these diagrams labeled PATEX API, fork, exec, and PO6 API. Wait,
Yeah,
are these the system calls that we've been talking about?
those are the ones. And if you look at the diagrams, you can actually see the function prototypes for these system calls.
Okay, so this is what it looks like in code.
Exactly.
All right, so we've got some code examples here.
Yes.
In listings 6 and 7,
Yeah.
and they show how to create a child process.
Right.
Execute a specific task within that child process.
Yep.
And then wait for it to finish using fork, exec, and wait.
That's exactly right.
And this is using C and Rust.
It is.
Okay, cool.
Yeah. And if you think about it, this is like a head chef giving instructions to their assistants, delegating tasks, and then waiting to make sure it's all completed before they move on.
Yeah, that's a great analogy. So listings 8 and 9, they take this a step further,
They
right?
do.
They're showing us how to create a basic shell
Right.
using these concepts.
Absolutely. So every time you type a command into your terminal,
Uh-huh.
this is basically what's happening behind the scenes.
Oh, wow.
You're creating this child process
Okay.
to execute that command, and the shell is waiting for it to finish.
Wow. So even something as seemingly simple as typing a command
Yeah.
into my terminal,
Right.
it's actually, this whole orchestrated symphony of processes happening in the background.
That's a great way to put it. Now let's shift gears and talk about threads.
Okay, threads.
Yeah.
I've heard that word before, but how do they differ from processes?
Yeah. So threads are like lightweight processes. They provide a really efficient way to achieve concurrency, but all within a single process.
Okay, so they're kind of like smaller, nimbler chefs.
That's a great way to think about it. Yeah. Okay.
So to understand threads, we need to understand context switching.
Context switching. Okay, this sounds complicated.
A little bit, but it's not too bad. So think of it like the CPU putting on a different hat
Okay.
for each process or thread that it's working on.
Okay.
And if you look at the diagram, context switch, it kind of illustrates this nicely.
Okay.
So each process or thread, it needs its own execution context,
Okay.
which includes things like the values in the registers, the program counter, information about the stack. And when the operating system wants to switch from one process or thread to another,
Right.
it needs to save all that current context and load the context for the new one.
So it's like changing costumes.
Yes,
Backstage during a play.
absolutely.
So that, each actor has the right, outfit and props for their scene.
That's a fantastic analogy.
Okay.
So now the problem is switching between processes, it's a bit of a heavy process.
Okay.
Because you're saving and restoring all that information.
Right. And that can really slow things down.
Okay.
So threads actually provide a solution for this.
Okay, how so?
So because threads share the same address space as their parent process, the context switching is much, much faster and much more efficient.
So it's like they're already wearing the same costumes.
Yes, exactly. It's like a quick change.
Yeah, it's like a quick change. Okay.
And so this makes threads extremely well suited for tasks that can be broken down into smaller independent units of work.
So threads are like a team of chefs
Yes.
working together in the same kitchen, sharing the same ingredients and tools.
That's a fantastic analogy.
So they can work more efficiently.
Exactly. And they can communicate much more easily. They can share data.
Okay.
It's a very streamlined workflow.
Okay, so how are these threads created?
Right. So there's a special system call for that.
Okay.
And it's illustrated in the diagram here, thread creation. Thread create. And this function is part of the PO6 threads API.
Okay.
And what this function does is it creates a brand new thread of control,
Okay.
but within the current process.
Okay.
So think of it like hiring a new chef,
Uh-huh.
but they're working in the same kitchen.
Gotcha.
So thread create will allocate a stack segment for this new thread, initialize it, and set it up so it can run independently.
Okay. So the new chef gets their own workspace
Exactly.
and their own list of tasks.
Yep.
But they're all working within the same kitchen.
Exactly, yeah.
Now, I see another diagram here, PBO6 API threads.
Yes.
So there's API functions for managing these threads too.
Absolutely.
Okay.
Yeah, and if you look at the diagram, you'll see some familiar faces like thread join, thread exit.
Okay, so thread join, it's like one thread's waiting for another one to finish its task.
That's right.
Before it moves on.
Exactly. And then thread exit, this allows a thread to kind of terminate gracefully, signal that it's finished its work.
Right. So it's like the chef's like, hey, I'm done for the day.
Exactly.
Okay, so we've got some code examples here for threads too.
We do.
Listing 10 and 11.
Yep.
And this is showing thread creation and joining in C and Rust.
It is. So in these examples, what we're seeing is that the main thread, it spawns these multiple child threads.
Okay.
Gives each thread its own task.
Okay.
And then it patiently waits for those threads to finish.
So it's like this really well-coordinated team.
It is.
Of chefs all working together.
Absolutely.
To create, a delicious meal.
Yeah, to produce something amazing.
Okay. So let's zoom out now.
Okay.
And talk about how this all fits into the grand scheme of the Linux kernel.
All right.
What's going on under the hood?
So in the Linux, both processes and threads are represented as tasks.
Okay.
So if we look at the diagram, processes and threads in the Linux kernel, it kind of highlights how tasks are represented using this task structure.
Okay.
And this task struct contains all the essential information about the task.
So it's like a detailed profile.
It is, yeah.
For each of these tasks, whether it's a process or a thread.
Exactly.
Okay.
And the Linux kernel, it maintains this list of tasks called the task list. And this is like a dynamic directory of every active task in the system.
Okay.
And to make searching and accessing tasks super efficient, it uses this really clever combination of a linked list and a hash table.
So it's like a really well organized filing system.
It is.
Okay. But what happens if you have, multiple processes or threads
Right.
all trying to access or change this task list at the same time?
Yeah, that's a great question. So if that were to happen, that could lead to some data corruption or inconsistencies.
Right.
So to prevent that, Linux uses something called task list lock.
Okay.
And this lock, this is essentially like a security guard. It ensures that only one process or thread can modify that task list at any given time.
So it's like a controlled access point to the filing system.
Exactly.
Okay.
Now, we've seen how these tasks, these processes and threads are represented, but how do they actually do things, right?
Right.
And this is where the system call table comes in.
Okay.
So think of this table as like a directory of services that the kernel provides. So each system call, like fork, exec, the ones we've been talking about.
Right.
They each have their own unique number.
Okay.
And a corresponding function pointer in the system call table.
So it's like a menu of services that the kernel offers.
Exactly.
With each system call having its own item number.
Exactly.
Okay. So when a user program wants to make a system call,
right,
the kernel uses that system call number.
Yeah.
To look up the corresponding function in the system call table.
Exactly. And then it executes that function.
Oh.
So it's like placing an order at a restaurant.
Oh.
The waiter takes your order number, finds the corresponding dish on the menu, and relays that request back to the kitchen.
Oh, that's a great analogy. So everything's very structured, very organized.
Very much so. It's a very clean, very efficient mechanism.
Wow. It's like a well-oiled machine.
Yeah.
Everything just works together in harmony.
Yeah, that's a great way to put it. Now, what if we wanted to actually observe this?
Okay.
Like this task management in the Linux kernel, like in action.
Yeah, can we actually see that?
We can. So if you look at listing 12.
Okay.
This is a code snippet. And it demonstrates how to iterate over all the tasks within the Linux kernel.
Okay, so let's break it down.
Yeah.
I see the first thing it does is acquire the task list lock.
Right. So this is that security guard that we were talking about for the task list.
Yeah.
It prevents other parts of the kernel from messing with the task list while we're looking at it.
Okay.
Okay.
So we acquire that lock, and then we basically traverse the list, accessing all the information about each task, and then when we're done, we release the lock.
Okay, so we have to be polite and unlock it.
Exactly.
So that other parts of the system can access it too.
Absolutely.
Okay, so this code snippet is kind of like a a sneak peek
It is.
into how to access and manipulate these critical data structures.
It is. It is.
Okay. Wow, this has been an incredible journey so far.
It has.
We've gone from like the basic definitions of processes and threads
Right.
to exploring, their life cycle, how they're created, how they terminate.
Right.
We even peeked into the inner workings of the Linux kernel
We did.
to see how it manages all these tasks.
It's amazing. It really is. The amount of stuff that's happening
Yeah.
kind of behind the scenes.
Yeah, and most people have no idea
Right.
that this is all going on.
It's quite fascinating. Yeah, it is. It's like we uncovered this whole hidden world
Absolutely.
of complexity
Yeah.
and ingenuity.
It's really quite impressive. So, as we've been, talking about processes and threads and all this stuff,
Yeah.
have you started to see your computer in a new light?
Oh, yeah, definitely. I used to think of it as like this magical black box.
Right.
I type something in, something happens.
Yeah.
But now I realize there's this whole like intricate symphony
Right.
of processes and threads happening behind the scenes.
Yeah, absolutely.
But I have to admit, I'm still kind of wrapping my head around the practical implications of all this. Like, does understanding these concepts actually help us,
Absolutely.
in our day-to-day use of technology?
Yeah, I think for starters, it can make you a more informed and a more efficient user.
Okay.